Thank you very much for the kind introduction. So the title was almost correct. So and then so it's two Littlewood type identities for fully inhomogeneous spin Hall Littlewood symmetric rational. The inhomogeneous is full. And the connection to ASMs.
So thank you for making this.
No problem, no problem. So no scared faces, but this will be. Oh, yeah, that was before the schedule was changed. I apologize deeply, but it's hard to change slides like this. So yeah. Since I will be talking about Littlewood identities, let's quickly recall the classical Littlewood identity, where on the left-hand side, we sum over all sure functions, and on the right-hand side, we have this rational function in the xi's, which I will call the Littlewood kernel. And now, and now I want you to recall two theorems and formulas we had seen in Ilse's talk before. These are some Littlewood type identities. And why do we call them Littlewood type identities? Because on the right-hand side, every time the Littlewood kernel appears, and there's just some addendum to the right-hand side. So on the upper side, we have these factors, and on the lower side, we have the partition function of the diagonally symmetric ASMs. And in the first theorem, we had replaced the sure functions by the Robbins polynomials, whereas in the second theorem, we had replaced the sure functions by the modified Robbins polynomials. And now what I will present, for the first few minutes, you have to just absorb, and then later on, I will go into details about what the polynomials are. Just note that these are all like some generalizations of sure functions. And we present an even more general two formulae. The first one is the following. So again, on the right-hand side, we have the Littlewood kernel, and we have this one additional factor of the 1 minus q ui uj. And this time on the left-hand side, we replace the sure functions by the fully inhomogeneous spin Hall Littlewood rational symmetric functions, which I will also define in just a second. Just absorb, again, generalization of sure functions, and in fact, some type of generalization of the Robbins polynomials, where also I will talk about the details later on. And then we have this normalizing factor of the Q Pochhammer symbols, where mr of lambda denotes the multiplicity of the part r of lambda. So this is the first formula, generalizing the first theorem on the previous slide. And then the second formula is again of Littlewood type, where on the right-hand side, this time we have an 1 plus q to the 1/2 and 1 minus q ui uj, and some Pfaffian, which I will also explain in a second what the m gamma is. Yeah. And then on the upper side, we have again the fully inhomogeneous Spin-Hall Littlewood rational symmetric functions and some normalizing factor. But this time, the multiplicity of the part 0 plays a special role and is normalized differently than the other factors. So don't worry too much about the details of the formulas. I know, quite intimidating at first because many factors and many things going on. Just note that some generalization of Littlewood type identities on the left-hand side, some normalizing factor of some Q Pochhammer symbols, times some polynomial, which generalizes sure functions. What that polynomial is and how that works, I will explain later on. And on the right-hand side, we always have this Littlewood kernel times some other factor. And in this case, the m gamma is this wonderful matrix. So again, as you can see, rational entries in the UIs and the UJs. And the 0 column, which is just there if n is odd, so that to make sure that the Pfaffian doesn't vanish, is different from the other columns. And in fact, if you look very closely, there's this FUI and this is on purpose printed quite small on this slide. Not too important. It's a nice expression, factorizes very nicely. So here. Yeah, that's the FUI that appears here. What do you mean by no S1? Yeah. F of U and B is defined like this. It's some expression. It's not complicated. It's factorizes it. Not too bad. Has some purpose. Just note that we can write it down, and That's the pattern. Don't worry about, you don't have to memorize this at all. Just note that. So, okay. And now I promised you to introduce the spin Hall Littlewood rational symmetric functions. But before we do that, I can already see some faces. Some people might think, okay, why is that interesting, right? But why should we care about this? Let me give you some ideas why you might want to care about this. So the F lambdas, whatever the F lambdas are, I will define them shortly. There were already some type of Littlewood identities and Cauchy identities in the literature, but they are of very different type. So it's not the Littlewood identity where you sum over all partitions, but where you restrict the conjugate of the partition to be even. So this is some new family of Littlewood type identities, and we also use some different proof methods. Then second of all, as I already teased, the F lambda generalizes the Schur functions as well as the Hall Littlewood functions. And in particular, if you specialize down to the Hall Littlewood functions, the second theorem gives you a completely new Littlewood identity for Hall Littlewood polynomials. Then third of all, as we will also talk about later on, the F lambda are closely related to the Robbins polynomials and the modified Robbins polynomials. So this gives you the connection to ASMs, arrowed monotone triangles, and down-arrowed monotone triangles. And in particular, this allows us to translate known identities from F lambda world to the ASM world. Like as we had seen in Ilse's talk, there was this Cauchy identity for the Robbins polynomials, which comes from this F lambda world. And we also get some new Littlewood identities for R and R star for free. And the nice thing about the R and the R star is that they generalize Grassmann-Grothendieck polynomials or symmetric Grothendieck polynomials. So you can also specialize all of these identities down to that level and get some new stuff over here. And for the people that know about this, F lambda is connected to ASAP and statistical physics. So you might also get some information for these words from all these formulas. And Littlewood and Cauchy identities are some hints for representation theory. So for the people that are interested in this, that could be a nice point to work on. And for me, most importantly, cool identity equals interesting. I like long formulas, so that's something. Okay, and now finally, I can tell you what the F lambdas are. For this, I have to introduce the higher spin 6-vertex model. So we are looking at some collections of paths where we have multiple up steps potentially per edge and only one vertical edge per edge. And in fact, we consider these paths in the upper right. Multiple up steps allowed per edge and only one vertical step. Horizontal, sorry. Or only one. Yeah, so like you can have like multiple steps per edge on like an up edge, like here, but you can never have multiple edges on the right side. So never multiple paths. Never multiple paths.
Paths may share horizontal. Vertical edges.
Yes.
Horizontal.
Exactly.
Oh.
And yeah, to some degree. And in fact, we look at those in the upper right quadrant of the square grid. So we index our columns and rows as follows. And the top boundary condition is given by some partition with potentially some parts equal to 0. And the left boundary condition is just all right steps. And now we want to count these things. So we give the vertex some weights. Again, not too important what the weights actually look like. Just note that position J contributes to Sj. So the columns are weighted by some Sj parameter, and the rows are weighted by some Ui parameter. And then the weight of the collection of paths is just the product of the weights of the vertices in the paths. Not too important what the weights are, just for completeness. And no, a priori, no. We will talk about this. But for the connections to Robbins polynomials, you need to make some specializations, and then there will be, but a priori in the full model. And then Borodin and Petrov introduced in 2018 the fully inhomogeneous spin Hall Littlewood symmetric rational functions. simply as the generating function of all possible collections of n upright paths in the higher spin-6 vertex model with top boundary condition lambda. And the n in this case is the length of lambda, where lambda may have some parts equal to 0, and it's also the number of variables. And then you have this infinite family of S parameters, which corresponds to the infinite problems that you can have. And in the same paper, they established this very important theorem, which tells us that this F lambda is actually of the form of antisymmetrizer divided by fundamental family. And now you might already somehow see some connection to the Robbins polynomials that we had seen before, because they were of a similar form, right? Yes, antisymmetrizer divided by some fundamental. And how this actually works out in detail, we will discuss soon. But first, I want to give you some idea of how to prove these theorems. So you can completely forget about the right-hand side of the theorems for now. So these were complicated formulas. Just keep one thing in mind: they were independent of the S parameters. So both of the right-hand sides, there were no S's equivalent. And what we want to do now is make use of this antisymmetrizer, because whenever you have an antisymmetrizer, you can make use of this antisymmetrizer recurrence relation, where you split off the last parameter or the first parameter or just any parameter you like, and then make use of this sum over the permutations. So you fix like one element that is mapped to something, and then you get, this signed recurrence relation. And in fact, what we have here are both the left-hand sides of the formula. So the first one was this sum over partitions times these Pochhammer symbols, and then the F lambda. And the second one was the a bit more complicated Pochhammer symbols, but of the same structure. Sum over all partitions, yeah, sorry. The H, this is just my notation for these things. That's, yeah, for the left-hand side. So this is just notation. And now we want to make use of this antisymmetrizer recurrence relation to derive a recurrence relation for the left-hand side. But well, we cannot only split of the last parameter as one we usually or in most cases do, because we are summing over all partitions and not strictly increasing rows. So the last part, so there may be multiple appearances of the smallest part of the partition, and we have to take account. We have to take this into account, and in fact derive a split of all of them at the same time. So how this works is you get this L, which corresponds to the smallest part of the partition initially, and then you get this T, where the size of the T corresponds to the multiplicity of the smallest part. Don't worry too much again about the detailed form. It's just a formula, and I want to give you some idea of what to make use, or how to make use of this formula. But what's important is that you get a recurrence relation from the left-hand side to the left-hand side in a restricted set of variables and a restricted set of the S parameters. And for the second thing, you can do the completely same thing, and you obtain two recurrence relations which are very similar, but there's a difference in the Q-Pochhammer symbols, which comes from the difference in the Q-Pochhammer symbols of the original formula. And otherwise, we can just square through the factors. These are equal, and these are equal, whatever they are. The only difference here is that the first recurrence relation relates the H1 to the H1, but the second one has the arbitrary gamma, but relates to gamma equal to 1. So this is not really what we want, right? Because if you want to make use of this recurrence relation, we want to plug in the right-hand side of the initial formula for the H's everywhere. And inductively, in fact, here we want to plug in the smaller guys and then show that they equal the bigger guys. But to plug in the inductively smaller guy here, we have to prove the formula for gamma equals to 1 first. So we do something similar related to which? The F numbers. The F numbers, the gamma in the second case just indicates the gammas in the Pochhammer symbols. So the gammas only appear in the Pochhammer symbols, not in the F numbers. So we do the same trick, but for the left-hand side, where we set gamma equals to 1. And then we get a recurrence relation which relates the H21 to the H21 on a restricted set of variables. So two very similar recurrence relations. How do we work with them? Well, now we plug in the right-hand side for the H1 and the H2, which are independent of the S's, as I told you before. And then we note that the only parts where the S is appearing are the parts colored in blue. The problem with these formulas beforehand was that we have this infinite sum, and that it's hard to evaluate this infinite sum if you want to sum over an expression like this. But now the nice part is that the N only appears in these blue factors, and in fact, the infinite sum can now simply be evaluated by a geometric series argument. This was because we restricted the Sj's to be equal to Sp after a certain cutoff point. So now the infinite sum, you just split off the parts which are smaller than P, and then you do geometric series and you get the second one. What you do next is you multiply with the denominator, and then you get something which looks like that. Okay, another very complicated formula. What's important are the parts in green. So on the left-hand side, you just win one factor, and on the right-hand side, you now have two sums which look very telescoping-like. And in fact, one can make use of this telescoping-like structure to show that this is equivalent to the following thing, where again, only the green parts are important. You get one more factor on the left-hand side, and here you lose any sum structure. So you only have to consider one sum overall, which reduces this to like a very, very basic level. And now the cool part is if you plug this in and do a few more like basic manipulations, bringing things to common denominators, we obtain these two wonderful polynomial identities. Very scary things at first sight. But let's take a look, right? We started with two completely different identities, and now we obtained two polynomial identities. Let's compare them one by one. So the left-hand sides, this is simply what's coming from the initial left-hand sides. They are different, but they share some common factors. But the most important thing is that here this pathing of the M1 appears, which makes the second equation much more complicated. Because if you remember the matrix, that was not easy. Yes, we're still talking about the H numbers. So yeah, this is what we did here. We used the recurrence relation, right? We want to use induction. So you assume that the smaller things are equal to the right-hand side, the smaller things. Yes, yes. So okay, let's come back to number one. Then on the right-hand side, yeah, this is how the proof works. We have to prove. Yeah, we have to prove. Sorry, we have to prove these two polynomial identities. So they are still to be proved. On the right-hand side, you get the sum over all subsets and some type of sign. And then you have these two different tuple functions again, which is obvious that they are different because you started with different ones in the initial forms. And you have these similar factors where the 1 plus q to the 1/2 appears on the right-hand side. These things are equal, and these things are also equal, but again, the path appears on the right-hand side because this is what we plugged in by induction. So two polynomial identities. And now if you remember, we did not want to prove the case m equals to 1, but the case, the case gamma equals to 1, but the case with arbitrary gamma. And now if we assume for a second that we proved this polynomial identity for gamma equals to 1 already, and then make use of this identity to deduce a polynomial identity which still has to be proven for the arbitrary gamma case, what we get is distant. This is already very fascinating because the only thing that changed is that a gamma pops up here and here. Everything else stays the same compared to the other recurrence relation, which is fairly non-trivial. Even if you do the calculations, there's no obvious reason as to why this should happen. And now you have two polynomial identities which you have to prove, right? How do you do that? Evaluations. And now the even more fascinating thing for me is both work at the same evaluations by very, very similar computations. So there's just some small differences in the arguments. But you evaluate them at the same points, and it works very similar. That's some type of miracle, because the formulas were like completely different, right? There's no reason as to why this should happen. And yeah, this is how the proof works. Now I can tell you the connection to ASMs and the Robbins polynomials. So a quick recap. We had seen the Robbins polynomials at t equals 0. This was given by this anti-symmetrizer formula and the combinatorial model where the arrowed monotone triangles, where the motto was errors are only allowed if you have a strict increase in that direction. And then you had sway. And now the modified Robbins polynomials are also given by an anti-symmetrizer formula. But the difference in that case is in the product, you throw out the diagonal factor and you throw out the -1 in the exponents of the xi's. And now that thing also has a combinatorial model, again for strictly decreasing bottom row. The so-called down arrowed monotone triangles. So this time, the directions are not above the entries, but below the entries. And the motto is an arrow is forced in a direction if the entries in that direction are equal. Otherwise, you are allowed, for example, you also have a vertical arrow, which is sort of the third possible declaration, which replaces the double arrows. This entry, for example, is forced because the proof is equal. And 3 has the freedom of having an arrow available. And now time limits. So yeah, I will talk a bit about the relationship between the fully inhomogeneous Hall Littlewood symmetric rational functions and the modified Robbins polynomials. So there's actually multiple ways to go from one side to the other side, but I want to talk about this particular one because this one also has a very nice bijective proof. So given some increasing bottom row or decreasing partition, we look at the spin Hall Littlewood function of lambda of the parameters u1 to un, and we set all of the column parameters, so all of the sj's, to -q to the -1/2, and then we do this rational transformation of the ui's into the xi's. And then on the right-hand side, what we obtain is the modified Robbins polynomial of the reverse partition, because we denote the bottom rows in increasing order, of x1, xn, and these two prefactors, which you can think of as some type of normalization factors. And in u, and w, where u is q to the 1/2 minus q to the -1/2, and w is q to the -1 minus q. So u and w are arbitrary. And there's enough time for I think. I don't say anything. 3 more minutes. Get a question said. So, okay, I want to give you a projection between this higher spin 6 vertex model and the down arrow monotone triangles in that particular case. So the important thing here is the weights at s equals to -q to the -1/2 for this particular configuration vanish. And what that means is, because at the end you have a partition with distinct parts, no two halves can share horizontal edge anymore because they have to split at the end for this partition. So this configuration would have to be. And now hope most of you have seen this picture at least once. So how to translate a Gelfand settling pattern into a family of paths. In this particular case, a monotone triangle into a family of paths. It's just that the vertical edges, so they give you the numbers of the corresponding row. So this two here corresponds to the top row, and there's 2 vertical steps in the second row with 2/6, and which is denoting down one by one. And this is basically the projection, but we have to make sure that the vertex weights and the decorations and the weights on the right hand side agree. So how do we do this? What we have to check is that the down arrowed entries correspond to vertices of that form, I purposefully hide the weights from you, but this in fact agrees with what the weights tell you. So we just check on the underlying object that this works. Now, this is quite a simple observation because if this vertex here, this is the same path, going through the vertex, and now both of these steps are in the same position. So both of these steps give you the same entry, but one of them in the row above and the second one in the row below. Now the only question is which so like if you count the paths from left to right, the how many path is it in each row? So like because there's a new path starting in each row, the ith path of the previous row then becomes the I plus first path of the row above. So you get you get an equality in that direction. And a similar argument works for the equalities in the other direction, but this time you have to have two different paths here. Because like if the pink path is the jth path in row I, then in row I plus 1, the red path will be the jth path because we just get one additional path, so the previous path, which was this mod 1. And now there's this prefactor coming in, and this prefactor in fact swallows some weight of one particular configuration each row. Don't worry too much about the details, but we can choose it so that it swallows the leftmost right angle configuration. And then the only entries that are left are those guys in yellow. And in fact, these are always pairs of one right angle leaving and one right angle entering. And the claim now is that these correspond to the sort of free configurations in the arrow monotone triangle. And they have to appear in pairs. So, because any path that enters in a row also has to leave the top. And the one path which comes neutrally in each row and leaves again was handled by the prefactor. So these always pair up. And now the vertical edge of the entering path gives you the special entry. This is rather clear because there's no equality to the left or to the right below in the monotone triangle because there's simply no edge underneath. If you have here, if you have this configuration, there can be no edge of a path here in this other configuration. And the most important thing is that these pairs of configurations, if you multiply the weights, they give you the freedom of choice of the weights for any of the three declarations. That was it.